All right. Okay. So we'll start with the lecture. I don't see many people today. Probably many in the expo, but I'm recording the class, so hopefully those that are not here will catch up later on. I wanted to give you some news. Let's see, PC. Why this is not working? All right. You can see that. Yes. Okay, so I told you that I will have my notes on PDF, but actually I was working a little bit during the weekend. Well, I was watching some tennis, and let me see if I remember correctly. If you go to this URL, I think it was, let's try that. No. Okay, just give me 1 sec, and I'll get that web page. So it should be github. Okay. All right, there you go. So the book that I'm writing now, it's online. If you go there, you'll find everything. So chapter 1, right? We already went through, and if you go here next, then you will see the same thing that I gave you, with the difference that I'm updating this one. So whenever if you send me an email, send me, hey, there is a mistake here, this number is wrong, or there is a typo. You will be able to see the updated version over here. And now we are somewhere over here in this chapter, and we talked already about stress. We talked about all of these, right? Remember that here in these notes also you have some examples, worked out examples that you can use for your homework. Actually, they are pretty similar. So you can find a guide there about how to solve some of the problems. And let's see, we are right now, we talked about lithostatic gradient, we talked about non-hydrostatic pore pressure, and I think the only one that we're missing here is one of the mechanisms of overpressure, which is this one, which I have right here, which I'm going to explain in a bit. But I just wanted to remind you that this is available, and I should be adding chapter number 3 today. I just have a few more things I have to finish, some of the work type examples, but then you should have that one ready too. And if you come back over here, you will see the next topic is horizontal stress, which is a very, very important one, okay? All right. So let's go to finish with overpressure. So can somebody remind me what are the sources of overpressure in the subsurface? Remember that we learned how to calculate pore pressure in the subsurface, and we said that sometimes can be hydrostatic, or many times it is not, right? So do you remember why sometimes pore pressure is not hydrostatic? Hydrocarbon generation, right? So when the organic matter cooks, actually some people tell that the source rocks, when they get to the right temperature, pressure, they call it the kitchen of the hydrocarbons, because that's where they are cooked, and then when they are released, and that creates a lot of overpressure. I have an example actually for that. It's a cool example. Not exactly related to cooking of hydrocarbons, but to how changes of pressure and temperature can cause overpressure too. No, let me wait. Let me wait for the example because it's linked to the other one. So, okay, overpressure because of hydrocarbon generation. What else? Diagenesis, the clay diagenesis, and the most important one that happens, I told you that happens a lot of offshore basins, young sedimentary basins. Tectonics also can cause some overpressure, but there was one more phenomenon that we talked a lot about that.
Change of temperature?
Yes, change of temperature, but we didn't talk a lot about change of temperature. If you remember, it was this phenomenon that we call disequilibrium compaction. Whenever we have sediments that have very low permeability and the rate of sedimentation is so high that pore pressure cannot escape out, then we have locked in pore pressure that dissipates as a function of time. And we calculated, if you remember, that sometimes it might take thousands of years for that pore pressure to go down. And that's the most important one, and that's the one that you also have in the homework. There's one example in which you have to work out, you have to calculate pore pressure based on the anomalies in porosity observed in a shale. Okay? Okay, good. So let's talk about the last phenomenon of overpressure. There are some others, but we just limit to this. And it is simply buoyancy. Let's imagine that we have a wellbore, and this wellbore is tapping into a reservoir. Which is somewhere over here. So there is a fault over there, and the wellbore is tapping into this oil accumulation. Let's further assume that, let's say there is a river over here, and that there is a connected path of hydrostatic pore pressure that goes underneath the oil accumulation. So as usual, we put depth in the vertical axis going down, and here we'll measure pore pressure. What is the pore pressure at this point? I'm telling you there is a connected path that goes from there to here. It should be hydrostatic, right? I mean, if there is a connected path, then it should be hydrostatic. And if it is hydrostatic, then you would expect that it's just going to, if we assume constant mass density, it's going to be a straight line that you can calculate with our formula, density of waters times G times Z. But what happens now if you go into the hydrocarbon region? And let's assume that this is gas. It's much lighter than water. As you go into the hydrocarbon region, and let's call this, let's say, a section AA. So we're going to measure pressure there at section AA. What do you think is going to happen with the pressure over here? This is something you learn in petrophysics, if you remember. You remember that when you get to the oil contact line or the gas-water contact line, you start to develop a capillary pressure. And the capillary pressure is a function of what? The what? Depth? But more specifically? Well, the water saturation is a function of the capillary pressure, but the capillary pressure is determined by something else. Yes. Yes, but here in this scenario, the capillary pressure is being imposed by something else. Then what the capillary pressure does on saturation, it's another thing. So let me, before we get to this example, let's go again to a swimming pool example. Imagine that this is filled with water, and you manage somehow to get into the swimming pool and to get a container which is full with air. We know that inside the swimming pool, the pore pressure is going to increase linearly, right? Outside the bucket. But what about inside? You think the pore pressure is going to change the same? No, right? It's not going to change the same because the density of this fluid is different. And inside this bucket, there is going to be a deviation. And inside the bucket, everything you feel is just a gradient. And the gradient here of vertical stress or pressure is going to be given by the density of the fluid itself. So if here I have air, which is much lighter than water, there's going to be a deviation that's going to make this gradient to be smaller in that region because the density is smaller. The smaller the mass density, the smaller the gradient. And that's what you see over here. And it's going to be exactly the same thing in this case. The gradient is just going to be given by the mass density of the gas, and it's going to look something like this. It's going to still increase with depth because gas has a density, but it's not going to increase as steeply as it would in the water region. So this difference over here, we're going to discuss in a bit, is going to result in a capillary pressure, as you told me before, and the difference is going to be proportional to the difference in mass density between the density of water, the density of the hydrocarbon, let's put it HC in this case, times G times what? What am I missing here? The height, very well. The height, which now I'm going to measure that height from the gas oil contact line to the top. And sometimes this can be a problem because if you're drilling a wellbore, imagine that you're drilling this wellbore through here, and you have another deviated wellbore that taps directly into the top of this reservoir. When you're drilling, you're feeling the hydrostatic pore pressure. You go through the shale, and if that's the cap rock, the shale cannot deliver a lot of water. So even if there is a high pressure, your drilling mine is not going to feel it. And you're going to think that more or less you're in hydrostatic pore pressure. But as soon as you get to the top of this, all of a sudden you're going to find a high pressure that might result in a kick. And the taller the hydrocarbon accumulation, the bigger the difference is going to be. And sometimes this kind of overpressure can be quite important, even to the level that it might result in some mechanical instability. We knew how to calculate pore pressure, right? And we know how to calculate pore pressure now in the context of overpressure, and we know also how to calculate pore pressure if there is another fluid in the reservoir. But we also learn how to calculate a vertical stress. So let's say the vertical stress, in this case, is this one. What would happen if more hydrocarbons continue arriving to this reservoir and it continues to fill up? What's going to happen to this line? Can you see, let's imagine this hypothetical gas-oil contact line. Can you see that if this one moves down, then now that deviation is going to start here? And what would happen if now the pore pressure touches the vertical stress line? Will fracture, and how will it fracture? That's one of the main things of this geomechanics course is try to understand better how rocks fracture in the subsurface. It doesn't fracture always the same. A hydraulic fracture is not the same as a fault reactivation or a shear fracture. You point to the right place. If pore pressure is too high and it gets closer to the total stresses, in this case the vertical stress, something is going to happen. We're going to have that overpressure that in this case is going to cause the rock to fail. How it fails, still we don't know that, and we're going to learn that, and that's where we're going right now, talking about horizontal stresses. I can tell you that, as we're going to see later, if our horizontal stresses are higher than the maximum vertical stress, if they are somewhere over here, if the pressure is able to get up to there, this is going to create a hydraulic fracture, which is going to be horizontal. It's going to be like a pancake. If not, if those horizontal stresses are lower than this vertical stress, and we're going to see the reasons why, before you get to there, very likely you're going to have a fault reactivation, and you're going to make this fault slide, and actually it should go like this. It will slide, and it will make those fluids leak through the fault. Okay, and so that's where I wanted to get with my next example. An example of overpressure in which we're causing rock failure. And this is when now we start to talk about horizontal stress. Okay, we already learned about pore pressure. We learned about vertical stress. One of the unique things of geomechanics is that at any given depth, instead of just having one value like say pressure or temperature, in order to define stress, you need at least 3 values, and you need at least also 2 directions that define where those values are. And this is what we're going to see right now. Okay, so again, we're dealing a wellbore in the subsurface. And we know that in this case, let's say we have a coordinate system 1, 2, 3, and now notice that I'm not going to draw in a square anymore, but I'm going to draw a cube because we need a cube right now. In that element of rock, I have a vertical stress, and also we knew that there we can have a pore pressure. So there is a pore pressure inside here. But also I'm going to have stresses from the sides. So before I draw those stresses, let's make an analogy with this. And we go to the seafloor again. And let's say that you get a pipe that goes from the seafloor, from the surface to somewhere close to the seafloor. And everything is full of water, right? Here's our whale. And you manage to stick to the end of the pipe a balloon. An empty balloon, okay? Now it's empty, and we're going to fill it up. If you inflate this balloon, what is going to be the shape of the balloon? It looks like a silly question, right? But you see it's not that silly. What do you think? I'm not talking about these balloons, you know, like the clowns use to make like the dogs, stuff like that, those long ones. No? Regular balloon. Like, what's going to be the shape of the balloon as you inflate the balloon over here?
It's bigger at the top first.
Well, let's assume the balloon is small enough that the pressure almost everywhere is the same. If I were to inflate a balloon right now here, what would be the shape of the balloon? Like an oval, or if I imagine like a perfect balloon, it would be like a sphere, right? And why inflates like a sphere? Because it doesn't have a preference to take a shape in any direction, because the pressure from all sides is the same. If you go to a swimming pool and also you try to inflate a balloon in a swimming pool, it's going to be a little bit harder because now you have additional pressure. But it's going to be, what do you say? Here, yes, it's going to be a sphere. So as you inflate the balloon, it's going to be a nice sphere. And that's because the pressure in all directions, from wherever you measure it, is the same, if we consider this as a point. We agree with that? You can see that, right? Okay, now let's take the same balloon, but in the subsurface with rock. Now we're going to try to inflate this same balloon over here. What is going to be the shape of the balloon? Let's imagine that this balloon is strong enough that can resist the rock, and it's not going to break. What do you think is going to be the shape of the balloon? Like what? Like, you mean like flat or like? Not flat, but ovally. Okay. So, well, I mean, let's say there are several cases, right? It could be like perfect sphere. It could be like a disc, right? Like a pancake, just in one direction. Let's say like this or like that. Or it could be like more like a tube, just preferentially growing in one dimension. So we have a sphere will grow in 3 dimensions everywhere. If we have like a disc, it will go preferentially in 2 dimensions, and the other one could be just growing just in one direction, like a tube. Which one do you think is going to be the case?
Last one.
Like growing like that in one dimension? Why that?
Because you have a maximum and a minimum horizontal stress as well.
Okay, so
So all the three stresses are different.
yes, and therefore?
Therefore, it will grow
Okay, you're pointing, you're getting close, but not quite dry yet. Any other suggestion? No? Anyone for extra points? No? Let's see, who doesn't have extra points here? Mr. Barmal is here? No, right? Mr. Boswell told me we'll be here. Miss Fang, you have, you Miss Fang? Yes. You have any suggestion? Like a sphere? Okay, we'll see that. So the answer is it depends. It depends on many things. Most likely it's going to be like a plate, like a disc. So for a moment, and now I'm going to add, as Mr. Wang said here, we have stresses that are going to be different in different directions. So let's add here, let's see which is the most convenient direction, but probably I'm going to say this is the maximum principal stress in this direction, and this is going to be the minimum principal stress in this other direction. So, and if I further assume in this case that SV is higher than SH max and higher than SH mean, the balloon is going to open like a disc and it's going to grow preferentially perpendicular to the minimum principal stress. So if I were to draw here, this is going to be like that, right? With long axis in this direction and with the short axis perpendicular to S mean. In this case, this is the minimum principal stress. And there is a reason for that. And the reason is that always a cavity, an opening in the subsurface is going to open perpendicular to the minimum principal stress. That's going to be the preferred orientation. And look, in this case, what is the minimum principal stress? Everywhere, right? So it opens in any direction. It takes also the shape of a sphere because that's the most energetically favorable configuration. It wouldn't take the shape of a square because that takes more energy. And this case is the same. It's going to open like this if SH mean is the minimum principal stress. You have a question?
Yeah. Why does it open kind of like this instead of just like as a tube like he said?
Because the opening doesn't care about which one is bigger, this one, SV or SH max. It just cares about this one, the minimum principal stress. And as long as it's doing work against SH mean, it doesn't matter if this one is bigger than that one or this one is bigger than that one. It just cares about that one. We're going to see later on that this is just a simplification and it's an ideal orientation that when S1 and S2 and S3, when these ones get close to each other, funny things start to happen, okay? But those ones, when there is a very small difference. Let's assume now that this one is much smaller than the other ones, and so it will open like a disc, perpendicular to that. And that's super, super important because this same balloon that we say over here, this can be a hydraulic fracture. So a hydraulic fracture would open always perpendicular to this minimum principal stress. And therefore, if you want to know in which direction hydraulic fractures go, you need to know what is the direction of the minimum principal stress, which is something that most times, if you go to a place where you don't know the stress field, that's something that you have to find out. Okay, so let's try to see all the cases possible for a hydraulic fracture to what will be the geometry based on the stresses, right? So in this case, we say that this is the direction of the minimum principal stress. But, for example, if now we have another case in which this one is SV, but now let's say SH mean is coming in that direction, and I have SH max coming in that direction, and let's change things. Let's change one more thing. Let's say that SH max now is going to be bigger than SV, bigger than SH min. What do you think is going to be the shape of a hydraulic fracture? We can now forget about the analogy of the balloon. Let's talk about hydraulic fracture. How is that hydraulic fracture going to open? Into the page. It's going to be always perpendicular to that one, so it's going to be something like this. It's going to be a plane like that. Okay? So I'm going to try to draw it now in 3 dimensions, but I might not be that successful. It's going to be something like this, perpendicular to S3. And what about if now I told you that SB is the minimum principal stress, SH mean is the intermediate stress, and SH max is the maximum principal stress. So in this case now, SH max is the largest stress, SH min is intermediate, and SV is the smallest. What's going to be the orientation of that hydraulic fracture? It's going to be a plane, horizontal, right? And it's going to open like this, perpendicular to S3. So you can see already from these 2 examples that I didn't tell you why these horizontal stresses could be larger than SV, but that can happen. Just trust me for some